In this video, we'll look at a last example on trigonometric substitution, and I would want to talk a little bit more about definite integrals and how we could do that or integrate or evaluate them. Now, imagine we are given this integral to evaluate from 0 to 3 root 3 over 2. This integral doesn't really look like what we used to, but we can transform it to what we need. So to do that, we can write this integral like, I want to try to write it as s squared plus something squared. So how do I achieve that? Well, I can factor out whatever is the coefficient of s squared, so it is alone. That means I can write this integral to be the integral from 0 to 3 root 3 divided by 2 of x to the power of 3 over, I want to factor out 4 from this. So I'm going to have 4 and then s squared plus, I had 9 here. Because there was no 4, this is going to be like 9 over 4. And then everything here is raised to the power of 3 over 2 dx. So this tells me that I would have from here, the integral is still going to be the same in terms of limit, x to the power of 3. But we'll look at something now. I have a product of two things. I can write this as 4 to the power of 3 over 2 multiplied by x squared. 9 over 4, I can write 9 over 4 as 3 over 2 all squared. And then everything here is raised to the power of 3 over 2 dx. Notice that 3 over 2, like if I have this radical expression, maybe a plus s squared to the power of 3 over 2, this is the same thing as square root of a plus s squared to the power of 3. So we have a radical expression, and that is why we are trying to use trigonometric substitution. So this is another way to write what we have here. Maybe I'll just write it that way. But okay, I'm going to write it that way. This would be equal to 4 to the power of 3 over 2 is same thing as square root of 4 to the power of 3, which is 2 to the power of 3, which will be 8. So here I'm going to have 1 over 8. I can write that outside. Integral from 0 to 3 root 3 over 2 of x to the 3 divided by, let me write this way. I think it's going to look better this way. 3 over 2 all squared, but everything here is raised to the power 3. Now this looks like an expression that I have seen before, and I'm going to make the substitution, letting my x to be equal to, what we have here is 3 over 2 tangent of theta, because we have s squared plus something squared. Now we find what the x is and what the expression under the radical sign simplifies to. So this tells me that my dx is going to be equal to 3 over 2 secant squared theta d theta, and the expression under the radical, I'm just going to simplify like the square root, because the cube of that is still going to be the same thing. So I'll simplify this, s squared plus 3 over 2 squared. That would be square root of 3 over 2 tan theta squared plus 3 over 2 squared. In fact, 3 over 2 squared is 9 over 4, so maybe I'll just write it as that. This will be 9 over 4 tangent squared plus 9 over 4. We can factor out 9 over 4 to get tangent squared plus 1. And my tangent squared plus 1, if you recall, is the same thing as secant squared. So we have 9 over 4 secant squared of theta, and we can now take the square root to get 3 over 2 sec theta. One other thing we need to change is the limit point. We are moving from x to theta, so we have to change the variables also. Now from s is equal to 3 over 2 tan theta, we get that tangent of theta would be equal to 2x over 3. So this tells me that my theta would be equal to the inverse tan of 2x over 3. So when my x is equal to the lower limit point, which is 0, I would have that my theta will be equal to inverse tan of 2 times 0 over 3 is just going to be 0, which is 0. When x is 3 root 3 over 2, I have that theta will be equal to inverse tan of 2 multiplied by 3 root 3 over 2 divided by 3. If you simplify what is in here, you're going to get inverse tan of 2 will cancel out 2 and 3 will cancel out 2. We are just left with this. Inverse tan of this. And inverse tan of pi of square root of 3 is same thing as pi over, I think that would be 60 degrees, yeah. Pi over 3 or 60 degrees. Yes. So moving on, we can now say that our integral, that integral actually looks too big. I'm going to call this thing here I. I'm going to say this is equal to I, so that I can be writing I to save some time. You can actually do this when you are doing your integral. My I would now be equal to, I got it to be 1 over 8 integral from 0 to 3 root 3 over 2 x cubed over square root of s squared plus 9 over 4 to the power of 3 dx. So if we make the substitution, we'll be having that the endpoint will be going now from 0 to pi over 3. And then my x was equal to 3 over 2 tan theta, so my x squared is going to be, okay, just going to have this. 3 over 2, that's not really s squared, it's x to the power of 3. Let me see the original problem. Yes, x to the power of 3. So I have 3 over 2 tan theta to the power of 3. My dx was 3 over 2 sec square theta d theta, so I have 3 over 2 secant squared of theta d theta. Everything here is going to be divided by what we have below. What we have below is this radical sign cubed. The radical expression simplifies to this, so we are just going to have this 3 over 2 sec theta all to the power of 3. Recall we have 1 over 8 here, so we'll still bring that down. Okay, now this looks like a bunch of, very many things, but maybe we can write them out one by one to help us see what can cancel out and what remains. So above, I'm going to have 3 over 2 to the power of 3 tangent cubed of theta multiplied by 3 over 2 secant squared of theta d theta divided by 3 over 2 to the power of 3 secant cubed theta. So 3 over 2 to the power of 3 can cancel out with this. So the constant left here is 3 over 2. If I multiply that by 1 over 8, I'm going to get 1 over 16. Tangent cubed remains there. Tangent squared here can cancel out 2, or secant squared can cancel out 2 secants, and we are left with only 1 secant below. So after cancelling out, I get 3 over 16. That is multiplying this here by 1 over 8. Integral of what I'm left with in there will be tangent cubed over secant theta d theta. I think it's easier if I can rewrite these things in terms of sines and cosine. Maybe that will make my life easier here. So this would be equal to 3 over 16 integral of tangent is the same thing as sine. So I'm going to get sine cubed. Actually, 1 over secant is the same thing as cosine, so I can write this as cosine above. So I'll have this over cosine cubed multiplied by cosine. Cosine is the same thing as 1 over secant the theta. So I have that one of my cosines will be leaving from below. This integral here becomes equal to see how we are careful going through this. Actually, if you don't take it step by step, you're likely to miss some details at some point, and at the end of the day, your solution will be wrong. Okay, so from here, I can make a trig substitution. Since I have something in terms of sine and cosine, or u substitution, I can let my u to be equal to cosine of theta. That means that my du will be equal to negative sine theta d theta. And if that is the case, maybe I should let everything to be in terms of cosine and then leave only one sine. Yeah, that means I can write this in as 3 over 16 integral of this. I think we learned this kind of technique before. So I have sine squared theta cosine, or sine please, all over cosine squared theta d theta. However, my sine squared is the same thing as 1 minus cosine squared, so I can write this thing here as 1 minus cosine squared, 1 minus cosine squared, and then multiply by sine of theta. So I have sine theta d theta here. So if I make this substitution, I have this. However, I only have sine theta d theta without a negative sign. If I multiply both sides by negative sign, so I have that u, or negative du, is equal to sine theta d theta. Next, we have to change our limit point from theta now back to u. So if my u is equal to cosine theta, when theta is equal to 0, u is going to be equal to cosine of 0, which is 1. When theta is equal to pi over 3, u will be equal to cosine of pi over 3, and cosine of pi over 3 is equal to 1/2. So now my integral, which I'll still call I, which we got at this level to be this, would now be equal to, when we make the substitution and change variables to u, integral from 1 to 1/2, according to what we got. 1 minus cosine squared would be 1 minus u squared. Sine theta, the theta is negative du, all over u squared. This can be written as negative 3 over 16 integral from 1 to 1/2 of 1 minus u squared all over u squared du. I can divide by u squared. If I divide by u squared, I'll get minus 3 over 16, 1/2. 1 over u squared is something as u to the power of negative 2 minus u squared over u squared is 1, and everything here du. I can evaluate that integral very easily to get u to the minus 1 all over minus 1 minus u from 1 to 1/2. Another way to write this is this: negative 1 over u minus u from 1 to 1/2. So evaluating this now, plugging in the endpoints, it gives me this. Maybe I open a big bracket. Yes. For 1/2, which is the upper limit, I'm gonna have minus 1 over 1/2 minus 1/2 subtracted from the lower limit is 1, so I'm going to have like minus 1 over 1 minus 1. If you simplify what we're having here, maybe let's just go through this long road, not skipping any step. We'll be having 1 over 1 over 1/2 is just negative 2 minus 1 over 2 subtracted from minus 1 minus 1, which we simplify to be equal to, I think I'm running out of space, so I may have to just skip some step at this point. Minus this is going to be negative 5 over 2 minus this is minus 2, minus here is going to be plus 2, and this simplifies to, what do I have, negative 3 over 16. What I have in here is going to be like minus 1 over 2. This is going to be 4, yeah, minus 1 over 2, which will be equal to 3 over 32 at the end of the day. Therefore, my very big integral that we are solving originally, which is this, over, I think that was 4, yeah, 4s squared plus 9 to the power of 3 over 2, the x is equal to 3 over 32, and this becomes our final integral. Yes, it's possible that you may have something integrals that are this long, but basically they are this long because I chose not to skip any step, and that way you can do this is solving it as a indefinite integral first and then plugging in the value of x at the end of the day. But that means you have to change your variable from u back to theta, from theta back to x, and you may not want to do that. So I think whenever you're solving trig substitution and it's a definite integral, it's easier to change your limit point as you change the variable, so that you don't need to go back and forth changing variables. However, if it's an indefinite integral, you must change your variable back to x when you are done integrating, and you can do that always by drawing a right-angled triangle. So with this, we've come to the end of this section 7.3 in trigonometric integrals. The next video, we start a new section that helps us to see another way to integrate some functions, specifically this time rational function of polynomials. So we see, like, if you have a polynomial divided by another, how do we integrate that? One way we can do that is by starting off with partial fraction. So our next integral will be integration by partial fraction, and yeah, check out the video.